Scientific notation. When we deal with really, really big numbers, like the population of Canada, 33 million. Now, this is really out of date information. I think the population of Canada now is about 39 million or so. But the point is even 33 million is a really big number. Or very small numbers, like 0.000385. Both of those numbers have a lot of zeros in them. And we don't want to have to write a bunch of zeros. So to save time and space, we want to find a different way of writing out really big numbers and really small numbers. Scientific notation is that way. Like if you take science and you talk about how many atoms there are in a human body, or the mass of an atom, or the charge of an electron, or the size of the sun, the distance between the sun and the earth. These numbers are either really, really, really massively big numbers or really, really massively small numbers. And in order to make that easier to write out, scientific notation is a nice shortcut. So, here's how we would write both of these numbers in scientific notation. I'll probably repeat myself once or twice, but here goes nothing. There's always one number before the decimal in scientific notation. So when we look at this number here, we start off with a 3. Then I'm going to put a decimal, and then we'll put the rest of the numbers. So it's going to be 3.3. And I don't have to put, because we're talking about a decimal now, I don't have to put any of those zeros after that. So it's 3.3 times 10 to the something. Now we're going to use our rules that we developed to figure out how many place values that's it, where it is. So it's right here, but it's coming from right here. So that's 1, 2, 3, 4, 5, 6, 7 spots. So that is 3.3 times 10 to the exponent 7. 33 million is 3.3 times 10 to the exponent 7. That's how we write 33 million. So today we're going to be taking regular numbers and writing them in scientific notation. Or we're going to be taking numbers in scientific notation and writing them as regular numbers. Now here's a really small number. 0.0000385. So when we look and we're going to write our first number, we're writing our first number that's not a 0. The first number that's not a 0 is what? 3. So we're going to put a decimal after the 3. How many spots did we move the decimal? 1, 2, 3, 4. So this number is going to be 3.85. And now it's a small number, so it's going to be times 10 to the exponent negative 4. Because the decimal is moved 4 spots for that number. So that's how we write a number that's small with scientific notation. And we can see with both the really big number and the really small number, either way, we're writing a lot less digits for these numbers, and it's a lot quicker to write these numbers, and that's kind of the whole point of this. We want to spend less time writing these numbers. Okay, now here are some more examples of numbers in scientific notation. 3.11 times 10 to the exponent 5. That's a big number. 6.028 times 10 to the 23rd power. That's another really big number. There's always exactly one digit, can't be a zero, then a decimal, and then after that you can have any number of digits afterwards. Now you're not going to write like 10 digits after the decimal. Even if there are 10 digits that aren't zeros, you're going to probably round it, I don't know, to the nearest 2 or 3 or 4. You probably wouldn't go much past 4. So now we've got 3 examples here. We're going to write each of these numbers in scientific notation. So let's start off with 17,000. Find the first number that's not a 0. 1. Put a decimal after it. And then what we'll have to do is count the decimal places. So we're going to have to write it out. So 1.7, we don't have to put the zeros that follow after the 7, times 10 to the exponent. Now we got to count how many decimal places did we move. 1, 2, 3, 4. So this is 1.7 times 10 to the exponent 4. That's how we write 17,000 in scientific notation. So next question, we find the first number that's not a 0, and that's this 5 right here. So we put a decimal after the 5. Now, I've said so far today, you don't have to write 5s in the beginning, or not 5s. You don't have to write zeros in the beginning, or zeros in the end. But if you have a 0 in between numbers, you have to write it. You can only leave out zeros at the beginning or zeros at the end. So this number is going to be 5.05 times 10 to the, now this is a small number, so the exponent will be negative. Negative what? Very good. So this number is going to be 5.05 times 10 to the exponent negative 4. All small numbers, that'd be numbers under 1, are going to have negative exponents. All big numbers will have positive exponents. So again, that number is 5.05 times 10 to the exponent negative 4. Okay, here we go. So remembering that we don't have to count zeros at the end or at the beginning, that means we could pretty much forget about these zeros. But the decimal is going to come after the first number. So it's going to come after the 3. So it's going to be 3.001 times 10 to the what? 8. 3.001 times 10 to the exponent 8. Anybody unsure about how we got that? This is where the decimal's going. This is where it was. 1, 2, 3, 4, 5, 6, 7, 8 spots. So it's 3.001 times 10 to the exponent 8. All right, let's do some more examples. Here, we're going to write these numbers in standard form. Pay attention to the word standard form. Standard form is just give me what the number is. None of the scientific notation stuff. So when we have 3.18 times 10 to the exponent 5, what I would do is write out 3, a 1, and an 8. Now, here's what we're going to do. We know that the decimal is here. But because the exponent's positive, we're moving to the right. How many spots? How many spots are we moving to the right? 5 times. So, 1, 2, 3, 4, 5. We have these empty spots. And in each of these empty spots, what do you think we're going to put? Zeros. So it's going to be a 0, a 0, a 0, and the new decimal is going to come right here. Now, what you can see is I've made a mess of this number. So when you write out these numbers, when you make a mess of your numbers, write out your answer clean. So this is going to be 318,000, just like that. So that's what that number is in standard form. So if it asks you to write a number in standard form, it's really asking you for something like this. What's the number look like when we think about a real, actual number? Okay, so let's try question B. 4 times 10 to the exponent negative 6. So it's negative. So which way are we going to move the decimal, left or right? Correct. So we're starting off with a 4. Here's the decimal, and we're moving 6 spots to the left. So that's 1 spot to the left, 2 spots, 3 spots, 4 spots, 5 spots, and 6 spots. So the decimal's going right here. How many zeros go between the decimal and the 4?
5.
Right. 1 here, 1 here, 1 here, 1 here, 1 here, and you'll put 1 in front. So there's 5 decimals, but 5 zeros between the decimal and the 4, and the 0 before the decimal. So the answer is 0.0000004. That's how we write 4 times 10 to the negative 6 in scientific notation. So as we can see, it's a whole heck of a lot easier to write this out than to write this out. And that's why we have scientific notation for us.
I'm just going to see what the measurement of the sun is.
Part C, write this out in standard form. So, 9.01 times 10 to the negative 8. Is this a lot less than 1 or a lot more than 1? Less, because the exponent's negative. That's correct. So we have 9.01, and we're moving the decimal 8 spots to the correct. 1 spot to the left, 2, 3, 4, 5, 6, 7, 8. Decimal going right there. How many zeros go between the decimal and a 9?
7.
Very good. So if we write this out as one whole cohesive number, it would be 0 decimal 1, 2, 3, 4, 5, 6, 7 zeros, then a 9, then a 0, then a 1. This is your final answer right here. So again, there's 7 zeros between the decimal and the 9. All right. Next example. Write the number that's 10 times as large as. So let's talk about just real numbers here before we use scientific notation. If I say that, I don't know, I've got 3 hats, okay? And Chase says, I've got 10 times as many hats as you. How many hats does Chase have?
5.
No.
30.
30. Because you take 3 and you multiply it by 10 and you get 30. So if Chase has 10 times as many hats as me, he's got 30 hats. So 10 times as large or 10 times as many means you multiply something by 10. Okay? So when we see a question like this, write the number 10 times as large as, and it gives us the number in scientific notation. What we're going to do with this number is we're going to multiply it by 10. You know why I love math? One of the reasons I love math is because lots of things connect. Now all of a sudden we've got 10 to the exponent 4 and just regular 10. This brings us back to the last couple of days, because now we have powers with the same base. What do you do with the exponents when you multiply powers with the same base?
They add.
Do you add them? Yeah, exactly. There's an invisible 1 here. So if you have 10 to the exponent 4 times 10, that's going to give you 10 to the exponent. Very good. So 8.6 times 10 to the exponent 4 is going to become 8.6 times 10 to the exponent 5. That's how you do that question. Really straightforward. If the number's are already in scientific notation, just add 1 to the exponent. Done. Okay? Now, what about if the number's not in scientific notation? What about if the number looks like this in standard form? 0 decimal 0.00072. Well, just a moment ago, I told you that I really, really, really adore math because lots of things connect. Well, we did a lesson in the decimals unit on multiplying by powers of 10. So if you multiply by 10, how do we move the decimal? To the left, to the right, and by how much? Very good. We're going to move the decimal one spot to the right. Chunk. Now the decimal's here. So now there's only 2 zeros between this decimal and the 7. So 0.00072 becomes 0.0072. And again, these are things that we could figure out without using a calculator. We're just using our rules for exponent laws we learned earlier this week, and we're using our multiplying by powers of 10, which we learned a couple weeks ago. So that's how we multiply or find numbers that are 10 times as big as. Now we're going to look at find the number that's 1/10 as large as. 1/10 as large. How do you think we're going to treat those numbers? When it was 10 times as large, we multiplied them by 10. When it's 1/10 as large, what do you think we might do?
You would add -1 for the exponent?
Yeah, you would. For sure. Absolutely. You're absolutely right. But can we think about this in general terms? How do we find the number that's 1/10 as large as? Okay, let's do another little kind of sidebar here. Let's do a sidebar here. Let's say that Sam has 40 anime books. Okay? Sam has 40 anime books. Okay? Robert has 1/10 as many. How many does Robert have?
30,
No,
20,
no,
10,
no.
5,
Love the guessing. No,
3,
no,
4.
yes. If it's 10 times as large when we're talking about the hats, we multiply by 10. When it's 1/10 as many, we divide by 10. So we take 40 divided by 10 is just 4. It's important to know that because it's going to make our next examples hopefully make as much sense as possible. 900,000. If we divide this by 10. Again, go back to the lesson on dividing by powers of 10. Where are we moving the decimal? Left or right, and by how much?
Left once.
Left once. So 900,000 becomes what?
90,000.
Beautiful. 90,000. We went from having 5 zeros after the 9 to 4 zeros after the 9. If the number's in scientific notation, this is 2.15 times 10 to the negative 12. What do we do with the exponent? Well, we're dividing by 10. So look at this as powers, same base. What do we do with those exponents?
Okay.
What's negative 12 subtract 1?
11.
Hold up. Negative 12 subtract 1.
Negative
13.
11.
Negative 13.
Thank you. It's negative 13. We're going again. We're seeing all these beautiful connections. This takes us back to our time with integers. Negative 12 minus 1 is negative 13. And it's 2.15 times 10 to the negative 13 is how we write that number if we're trying to find the number 1/10 as large as 2.15 times 10 to the negative 12. Right? In summary, when you want to find a number that's 10 times as large, move the decimal one space to the right or add 1 to the exponent if the number's in scientific notation. If you want to find the number that's 1/10 as large, move the decimal one space to the left or subtract 1 from the exponent if the number's in scientific notation. That's just a summary of what we discovered on the previous page. Now we're going to multiply and divide these numbers in scientific notation. And let me caution you, okay? When students aren't sure of what to do, what they'll do is they'll just punch this number into a calculator right here. Or they'll write it out in standard form. And they'll then they'll write multiply and they'll write this number out in standard form. We're not going to do that. It's a colossal waste of time. What we're going to do is we're going to understand what the operation is. It's multiply. We're going to look at the numbers we're going to multiply, which is 3.5 and 2.1. And we're going to start off by multiplying those numbers. I don't expect you to know that without a calculator. So help me out here. What's 3.5 times 2.1?
7.35.
Sweet. 7.35. And then we're going to worry about the powers. We've got 10 to the 7 times 10 to the 5. When we multiply, we do what with exponents? So it's going to be times 10 to the what? Very good. So we get times 10 to the exponent 12. So that's what we get when we multiply two numbers in scientific notation. We take this number, multiply it by this number, figure out what we get. Then we multiply the two powers together, simplify the exponent, and that's it. Next question. 9.2 times 10 to the negative 3 divided by 2.3 times 10 to the exponent 7. Okay, this question's different. Why is it different? It's different because the base operation is division. So we are going to be dividing these numbers, not multiplying them. And we're going to be dividing these powers, not multiplying them. So, what's 9.2 divided by 2.3? What's 9.2 divided by 2.3? 4. Understanding we're dividing. What's 10 to the negative 3 divided by 10 to the 7? What's 10 to the negative 3 divided by 10 to the 7? Be careful. Use your knowledge of integers, which we touched on at the beginning of this term. What do we get? It's going to be times 10 to the something.
Negative 10.
Negative 10. Very well done. Because it's negative 3 minus 7, which is negative 10. Indeed. So the answer is 4 times 10 to the negative 10. All right, a couple more examples. Here's a good one. 4.8 times 10 to the negative 8 times 6.17 times 10 to the negative 3. Again, we're going to start off by looking at what the base operation is. Then we're going to multiply those numbers. And we're going to multiply these powers. So let's multiply the numbers first. What do you get when you multiply those numbers?
29.616.
29 point what, sorry?
616.
Okay. Times 10 to the exponent what?
5. Negative 5.
Nope. Now, you might have missed this. That's a negative 8. This is a negative 3.
Negative 11.
Negative 11. Nice. So that's good, right? Not quite. Here's the difference. There's nothing wrong with this, by the way. It's just it's not done. It tells us to write these answers in scientific notation. Why is this number here not in scientific notation? What's wrong with this number? There's 2 digits before the decimal. That's bad. You can only have 1 digit before the decimal. So what we have to do is we have to take one extra step and we have to put this in scientific notation. So think of this as a balance. Because what we're going to do is we're going to make this 1/10 as large, which is what we just did those examples on. And we're going to make this, the power, make this 10 times larger. So in order to do both of these things, we're going to move the decimal over to go between the 2 and the 9. And at the same time, we are going to, if we made the first number smaller, we have to make the exponent bigger. So we're going to take this exponent and add 1 to it. You have to do those things together. You have to make one of them smaller and one of them bigger. So this is going to become 2.9616 times 10 to the what?
Negative 10.
Negative 10. And that's your answer in scientific notation. You're going to get questions like this in your homework. And when you find out your answer, you're going to have to decide, is this in scientific notation or not? And if it's not like this one, you have to put it in scientific notation. And if you don't, then your answer is not fully simplified. So please try and make sure to remember to put those numbers in scientific notation. One more example. This time we're going to divide. So because we're dividing, we are going to divide 5.1 by 6.8, and then we're going to divide those powers as well. So what's 5.1 divided by 6.8?
3/4, 0.75.
Great. 0.75. Now, it's going to be times 10 to the something. To figure out the something, because we're dividing, you're subtracting the exponents. The first exponent's a 14, the second exponent's -8. What do you get when you subtract those exponents?
6.
No, sir.
22.
22. 14 minus -8. Is 22. So our exponent is 22. But the party isn't done yet because the digit before the decimal can't be a 0. So what we have to do is move the decimal one spot to the right to make this bigger. So if we make the number in front bigger, we have to make the exponent smaller. What do we have to do with the 22?
Take away 1.
Take away 1. And that's going to give us 7.5 times 10 to the exponent 21.